Okay, so picking up part 3 of notes 4-2 here. We'll pick up with this quick concept check and then move on. So a spring-loaded gun shoots a plastic ball with a speed of 4 meters per second. The spring is compressed twice as far. What does that do to the ball's speed? Well, this one really, hopefully, as soon as you identify the relationship, right? Again, I'm taking my elastic spring potential energy and I'm converting it to kinetic energy as the ball is fired. So I've got 1/2 kx squared equals 1/2 mass times velocity squared. Right, so what I would do in approaching this problem is just think about what does and does not change. Obviously the 1/2 can cancel out right now, but the mass of the ball and the spring constant aren't changing, right? So those are really constants as well, so they're not really relevant as I explore this consideration of when I compress it twice as far. So if I compress it twice as far, because I'm doing 2 times the displacement, so 2 times x, but then I'm squaring it, I'm actually making the left-hand side 4 times bigger than it originally was, right? So what do I have to do to the velocity so that it also becomes 4 times bigger? Well, really, then I just have to also double my velocity, because once again, since I'm squaring the velocity, if I double the velocity, I'm actually increasing this side by a factor of 4. Right? So there's a couple different ways you can think about that. We do end up just doubling the velocity. So if I've compressed it twice as far, then the speed will be twice as great. So it would be 8 meters per second. So again, if you can think it through in this regard, that works. The other way you can think about it, again, if you know that 1/2 kx squared equals 1/2 mv squared, focusing on what doesn't change, so the 1/2s are gone, the k and the m are gone because they don't change. If x squared equals v squared, then doesn't that tell us that x equals v? So what that tells us is those two are directly related, right? Whatever x does, that same thing has to happen to the velocity. And I should say equals very carefully here, right? These aren't necessarily equal, but they are proportional, right? So x squared is proportional to v squared. So then x has to be proportional to v. So once again, whatever I do to x, I have to do the exact same thing to the velocity. But anyway, hopefully this question's not too bad to get. Okay, so then the last couple examples we have to look at here just involve our energy diagrams. It'll take a slightly different perspective on these, but hopefully you guys agree it's not a terrible approach to it. So as I look at these energy diagrams, the line here is showing me just the total energy. So this kind of reddish line right here is showing me the total energy of the system. And then the blue curve is representing the potential energy of the system. Right? So obviously this isn't just a spring. If this was just a spring, we would expect the system to be more of a parabola, right? It would end up oscillating back and forth. So if this was a spring system, then my graph would look something more like this, where my total energy was a straight line here, and then my potential energy curve would intersect at those two ends, right? So this is some type of non-uniform system, right? It's got various different oscillations, various different motions throughout it. But it still is very important that I interpret what's going on, right? And I know you guys have a couple other graphs on your handout that you can kind of read through as well. But if I look at this one, well, what this tells me is, again, the blue line is representing the potential energy. So if I ask you to find the kinetic energy at any given point, how do I find the kinetic energy? Well, if the blue curve is representing the potential, then for instance at x2 here, the potential energy would be represented by whatever number value this is. The kinetic energy would be the remaining energy in the system. So whatever difference I have between the total energy up here and that point, that would be my kinetic energy. So I could do that at any point along the way, right? The kinetic energy is essentially what's remaining. So then that's where if I start to look at this graph, it tells me a lot of information. The first thing, as we can see that it identifies up here, it tells me when the system would be at rest, because I know that when all of the energy is potential, so anytime this blue curve intersects the red line, then all of the energy is potential energy, and therefore there's no kinetic energy. And if there's no kinetic energy, right, if the kinetic energy is equal to 0, then that tells me the velocity is equal to 0. So at those instances, the object is at rest, right? So on the other hand, when is the kinetic energy or when is the speed the greatest? Well, the kinetic energy and the speed would be the greatest when the potential energy is the least, right? So down here, I've got no potential energy. So then all of my energy would be kinetic, and therefore it would be the highest speed, right? And then obviously we have any point along the way where you could find it as long as you know those values. So do start to get comfortable. You'll notice as you go through the homeworks that you have several of these examples, but do start to get comfortable kind of interpreting these graphs. The one last thing that I will throw in on these graphs, the turning point. So the turning point is going to be any point in which the potential energy again intersects the total energy. So I may come over here to the graph that I drew to illustrate a spring, right? But if we think about a spring, we know a spring would oscillate back and forth between its motion, right? So here it's been compressed, it goes through equilibrium, it stretches a little bit past that, and then it turns around back and forth and back and forth and back and forth, right? This would represent a spring, and these would represent the 2 points in which it turns around, because again at that moment we know that it momentarily pauses, its velocity would be 0, and then it comes back the other direction. So for what it's worth, if I look at a graph like this first one, these two parts of the curve that extend beyond the total energy actually don't have any physical meaning, because the object will never pass this location right here or this location right here. So turning points are something you should become familiar with as you look at these graphs. Again, hopefully as you look through the homework you guys will agree there's nothing too tricky about these, but it is worth spending a little bit of time on to make sure you're comfortable with it. But anyway, let's do a little bit more then with these graphs to make sure you guys feel good and comfortable with them. Right, so any local minimum and maximum in the graph does indicate a special position for us. Right, so if I look at the following diagram down here, they give me a couple different various energy lines. We'll talk about that a little bit more in just a second. But the two terms that I do want you to start to get comfortable with are these two here. So feel free to pause this and make a note of these two. I know they're on your handout as well, so maybe just kind of star them or bring your attention to them. But stable equilibrium is an equilibrium position for which small disturbances would only cause small oscillations, and that's represented by any minimum on a graph. Unstable equilibrium, a point of equilibrium at which even a small disturbance will cause the particle to move away from the point. That would be any maximum. So again, pause that if you need to write any of that down, if you want to make any notes, but I'm going to go back up to the graph to reference those. Okay, so if I asked you to find the stable equilibrium on this graph, there would be 2 points of stable equilibrium. It would be this second position x2, and it would be this fourth position over here at x sub 4. The reason that those are stable equilibrium is because, again, they are the minima on this graph. And why is that stable? Well, that's stable because if I were to add just a little bit of energy to the system, right? So if I added just a little bit of energy, then what's going to happen with that point? Well, that point would oscillate maybe this way or to the left. It would oscillate up a certain distance, but if it didn't make it over this hump, it would then just continue to oscillate back and forth and back and forth, right? So it doesn't actually then leave that equilibrium position, right? It just kind of oscillates back and forth between. Same thing down here. It takes a lot of energy. I'd have to add at least this much energy to the system in order for this point right here to break free of this oscillation, right? If I added this much energy, then that point, that particle would just oscillate back and forth and back and forth and back and forth, right? So that's why those 2 points are referred to as stable equilibrium, because their tendency is to continue to oscillate around that equilibrium. On the other hand, up here, right, if I were to place a particle exactly at that point, so if I were to place an object right here and it wasn't in motion, then yes, it would remain at rest right there. It would not move, it wouldn't go anywhere. But if I add even a little bit of energy to the system, well, if I add or take away any type of energy at all, then that object's going to go either down on the right hand side or it's going to go down on the left hand side, and it's going to fall out of that equilibrium position, right? If I'm looking at the top of that curve, then if the object were to oscillate either direction at all, then it's going to go way down here or it's going to go way down here, and it's not going to make it back to that position, right? So that's why this is referred to as unstable equilibrium. Currently it is in equilibrium, all the forces are equal to 0, right? It is balanced out, but it would not remain there if we had any type of change in velocity or change in energy, right? So that's why it's referred to as unstable equilibrium. So I do expect you guys to get pretty comfortable identifying those. There are several homework questions that will ask you to do that. There are several homework questions that ask you to kind of start interpreting these graphs. Again, if and when you have trouble when you get to those, just let me know so I can help you through it. Right. The last example that I did throw onto this example page, actually a little bit of a sidestep, so it doesn't have to do with the graphs that we just looked at, but it is a good one to make sure you're comfortable with. So we've got a spring that has an initial length of L sub 0 and a spring constant of K. It's standing on one end. A block of mass M is placed on the spring, compressing it. What is the length of the compressed spring? Right. So the only difference that I do have to be careful about here is it's actually not asking me how far is the spring compressed. It's asking me what is the length of the spring after it's been compressed, right? So if I think about this again, I've got a vertical spring, and then I'm placing an object on it, right? So a block of mass M is placed on it, compressing it. Well, when the spring compresses, right? When the spring compresses, what's happening in terms of forces, right? So I want to think about this because I know that at that maximum compression, the object and the spring are going to be in equilibrium. There's not going to be any net force, right? So what are the only forces acting? Well, I have the force of the gravity pulling down on the box, and I have the force of the spring pushing up on the box, right? Again, when it's at its maximum compression, I know that those two forces will be equal and opposite. So I really then know that my force of the spring is equal and opposite to the force of gravity. Well, from here, my spring force is just kx. My gravitational force is mass times gravity. So I obviously can solve for my x. X equals mg over k. Once again, the biggest thing I have to realize is this simply represents my delta x. It represents my change in x. It doesn't actually represent my length of the spring, right? So if my original length of the spring was L sub 0, and I know that it is now compressed a distance of mg over k, then the new length of the spring would be my original length L sub 0 minus mg over k, right? So this question, hopefully not too bad here, but it is very important that you once again start to get comfortable manipulating these equations, even if we just have variables, right? So even if there aren't explicit numbers to plug in, you should start to get comfortable manipulating these equations. But anyway, this will finish out then example page 4-2. Like I said, if you guys do have any questions, any hesitancies at all, just let me know so I can help you through them. But hopefully this section wasn't too bad. There was a little bit of calc early on, and then in part 2, that lab question may be the trickiest questions. But let me know if you have any other questions or concerns.